Physical geology students. This is the second video for Wednesday. It's going to be called Summer 24. I'm going to put out probably 2, maybe 3 more videos for this week. So keep your eye out for those. I hope you subscribe to the YouTube channel so you can keep getting these. We were on Chapter 7, talking about the principles of relative dating. And sorry, my hair is standing up. I just washed my hair. Let's see. Where am I here? I want to float the top. So, all right. So, bottom line is, we talked about the principles of superposition, principle of original horizontality, the principle of lateral continuity, the principle of cross-cutting relationships. Next one we're going to talk about is the principle of inclusions. All right. And then I'm going to show you how to actually use this. Because if you actually do this, you'll understand it a lot better. I remember when I was a little kid, my father would say, well, to change the oil, you got to get under the car, and you got to get an oil wrench, you got to take the old filter off, and then you have to get you have to drain the oil. You know, that's all words. You got to actually, when we got under the car and changed the oil, then I really understood it. So we got to change the oil. We got to use this stuff. But first, let's talk about it. Principle of inclusions. All right. Now, first of all, in order to understand the principle of inclusions, you need to know what an inclusion is. Here's a picture here. I want you to take a good close look at this picture. At first glance, these two pictures might seem the same. Here you have a sandstone, a sedimentary rock, a detrital sedimentary rock, and it's represented by these dots. Then in orange, they have granite, which is an igneous rock. It's a plutonic rock. You have the same thing on both sides. No, you don't, because in this picture here, you have inclusions of the sandstone in the granite. An inclusion is a chunk of rock that has been incorporated into another rock. And we'll take a look and see how that happens in a moment. But on this side, notice that you have inclusions of the granite in the sandstone. Ladies and gentlemen, the principle of inclusion states that the rock that contains the inclusions must be younger than the rock from which the inclusions are derived. I'll repeat that. The rock that contains the inclusions is the younger rock. So, in this situation here, which rock is younger, the granite or the sandstone? Well, if it was sedimentary rocks, we could just say principle of original horizontality. The one on top is the younger one. But now we're dealing with igneous rocks. We can't do that. We have to look at the inclusions. So which rock is younger in this case? The granite is younger than the sandstone. And in this situation, the sandstone has the inclusions of the granite, so the sandstone is younger than the granite. Once I describe how this occurs, I think you'll understand how the principle of inclusions works. In this situation, the sandstone was deposited maybe in a river, maybe on a beach, maybe in a desert. Those are typical depositional environments for quartz sandstone. Then later on, the granite cut through the sandstone and removed chunks of the sandstone and incorporated it into the magma chamber. The sandstone, these fragments, which we call inclusions, did not completely melt. There wasn't enough time to melt them, so they were included within the granite. In this situation, we had granite intrude into some rocks that are no longer there, but because granite, you know, is plutonic, is a phaneritic texture. So it cooled underground somewhere and penetrated some rocks which are no longer there. Then those rocks were removed by erosion, and then maybe you had a beach or a desert come over here, let's say, or a river, let's say it was a river, then the river would have torn up chunks of the granite and incorporated it into the riverbed, and so you have inclusions of the granite and the sandstone. See if you could describe that in your own words. But for now, just remember the rock that contains the inclusions is the younger rock. The last principle of relative dating is the principle of fossil succession. And this one came from William Smith, an Englishman. And in order to understand the principle of fossil succession, we have to remember that William Smith was a contemporary and a friend of Charles Darwin. Charles Darwin is the founder of the theory of biological evolution, which is the basis of modern day biology. I mean, species change. The fossil record clearly shows it. Having said that, it doesn't. People make political hay out of this. It's not. It doesn't mean that there's not a creator. I happen to believe there is a creator as a Christian. Darwin was not an atheist. He said that his theory of biological evolution did not prove or disprove the existence of a creator. All it says is that species change, and only the strongest survive and pass on their genetic information, which we now know as DNA. And if you look at the fossil record, we can see this. You can see here in this picture here, these creatures here lived in at a time more distant in the past, and then these in a slightly more recent time, slightly more recent time, and he would find this succession of fossils in England. You know, the United Kingdom has, in the 1800s, included Scotland, England, Wales, and Ireland. So he went to Scotland and he found the same succession of fossils. Only, maybe a little difference because this one here is not located in England, but it's only in Scotland. But you see the same succession of fossils. And then you go to Wales and you see the same thing. You went to France, Germany, Japan, Australia. You always see the same succession of fossils. That's how principle of fossil succession shows us that we can use fossils to date rocks, because certain species only live during certain parts of geologic history. So we can actually date rocks by using fossils. And so let's say that this is in England and this is in Scotland. We could say that this bed contained the same fossil as this bed, so it formed at the same time. And then this and this, and then this and this. So principle of fossil succession is important because it shows that Darwin's theory of evolution works. We could see the species changing with time. We could see that even with humans. Humans 10,000 years ago looked much different than they do today. And many of those bloodlines have died out because if you don't have what it takes to survive in the world around you, and you have to do two more things to pass on your genetic information. You have to attract the opposite sex and produce fertile offspring. If you can't do all three of those, your genetic information does not get passed on. That's just common sense. And we can see that in the rock record. Now let's use these tools that we've now got in our tool belt. These 6 rules of relative dating. And I'm going to show you how to do this. And this is going to help you for next week's lab. Okay, let's do some relative dating exercises. Let's get under the car and change the oil. Let's start off with something very simple. This is about as simple as you can get right here. And now now my job here is to do the relative dating. I need a new note here. To do the relative dating for this cross section. So this is what we see of the rocks. We have layer B, and on top of it, we're looking at it from the side view. Then we have layer C on top of it, and layer D on top of that, and layer E on top of that. Okay? Those are sedimentary because they are layered. A, on the other hand, is igneous because it cuts through these sedimentary rocks. Also, um, dots means quartz sandstone. Dashes means shale. A brick pattern like this is called means limestone, and then you got another sandstone here. And this is a plutonic rock. It's a dike, and it's cutting through beds B, C, and D. So to tell the story of relative dating, you have to say what happened first. Well, bed B was deposited first, right? Isn't that the first thing that happened? And notice that when we do relative dating, we always put the first thing that occurs on the bottom. And I hope you remember that because people always forget this. Some people do. So the first thing that happened was bed B was deposited. Then the second thing that happened is what? You tell me. Bed C was deposited, or bed C, or the shale was deposited, was deposited. Then what happened? Third thing that happened is what? The limestone. Bed D was deposited. Then what? Oh gosh. See, it won't let me do it. Okay. I hate this crap. Let's see. Let me get Microsoft Word. Okay. Let's just go to Microsoft Word here. All right, and I'm going to make a new document here. Okay, so the first thing that happened was we put that on the bottom. Bed B was deposited. Then what? Then you go up to the next one. 2, bed C was deposited, which is the shale. Then what happened? Bed 3 was deposited, or bed D was deposited, which is the limestone. And then bed E was deposited. E was deposited. Then what happened, ladies and gentlemen? You tell me. Then dike A cut through beds B, C, and D. That's the relative dating for that. That's about as simple as you can get. Look at that picture and see if you can get this exact answer. And that's step number 1. Now let's do something more complicated here. I don't want to get too complicated and scare you away here. Let's do let's see here. Okay, next thing we want to know, before I can go to the next step and do something like this, okay, we need to know what a wavy line means to a geologist, okay? We need to know what this wavy line is. It's not always going to be in red. Here you can see, here's one wavy line, here's another wavy line, here's another wavy line. Okay, those wavy lines, we need to know what that is before we can take the next step and do more complicated relative dating. Now, those wavy lines are called unconformities. Whenever you see a geologist drawing that wavy line in the cross section, that means an unconformity. Here's an unconformity here. Now, the man who discovered this, what an unconformity is, His name is James Hutton, and the same guy who came up with the principle of uniformitarianism. This guy's amazing, all the things he learned. And he discovered it right here in Scotland, at Sicker Point. Scotland's beautiful. You go to the UK, don't just go to London, take the train north to Scotland. It's beautiful. Here you can see where these four people are standing, the exact place where James Hutton was confused, and then he figured out what this was. Here you see sedimentary beds that are tilting at an angle, going like this, but we say dipping. So here we see sedimentary beds dipping at this angle. Then there's some kind of wavy surface here, and then above this wavy surface, the sedimentary beds are dipping at a different angle. And James Hutton was standing here, and he was wondering, looking at this puzzle, figuring what's going on here? Why are the beds dipping this way and then dipping this way, and there's a surface in between? He was probably saying something like this: "These beds are dipping this way, and they're dipping that way over there, and it's colder than the witches." It's never mind. So he quickly realized that principle of original horizontality tells us that these beds were originally horizontal, and then they must have been tilted by an earthquake. Then this surface here, which he called an unconformity, is an erosional surface. That's why it's wavy. It's not a straight line. So the only way you can form this surface in unconformity, and this is hard to imagine unless you understand geologic time, is if the land was uplifted. That means it was lifted up to a higher elevation. That's what we call mountain building. And then those rocks were eroded. Okay, so the nonconformity represents the uplifting of a mountain range or a small mountain range or a big mountain range, and then the erosion of those rocks, the erosion of these tilted rocks. Then later on, these flat rocks were horizontally deposited on top. That's an unconformity, ladies and gentlemen. Whenever you see a wavy line, a geologist shows you a wavy line, what he or she is trying to show you is that, let's see, a wavy line, that means uplift and erosion occurred. And James Hutton realized, going back to that picture of Sicker Point, that how much time must go by to form an unconformity. You have to have a mountain range raised out of the ground and then be eroded away, and then new sediments deposited on top of that. Well, think about the Appalachian Mountains for a moment. They're 290 million years old, and they're still here. True, 290 million years ago, they were 3 times as tall as now, but it's going to take another 100 million years before the Appalachian Mountains are eroded flat, like Kansas. And then if new sediment is deposited on top of that surface, then you have an unconformity. So another way of saying it is, this unconformity surface represents way more time than all of these rocks above and below it. And that's why James Hutton realized that the Earth must be incredibly old. To form an unconformity takes an unimaginably long amount of time. Next thing we want to know is there are 3 kinds of unconformities. Okay, you need to remember the 3 kinds of unconformities, and they are a angular unconformity, a nonconformity, and a disconformity. You need to know this so you can do the next lab. These are the 3 kinds of unconformities. You need to be able to look at that wavy line and figure out which type of unconformity are you looking at. Angular unconformity, nonconformity, or disconformity. There's no such thing as an angular disconformity. Okay, let's take a look at an angular unconformity here. An angular unconformity is an unconformity. Okay, this is a cross section, but it's in a block, so we call this a block diagram. This block diagram shows you a side view of the cross section over here too. But with an angular unconformity, you have sedimentary rocks dipping. Angular unconformity. You have sedimentary rocks above and below the unconformity surface because there are layered rocks above and below. But the sedimentary beds below the unconformity surface are tilting at an angle. They're not horizontal. The sedimentary beds on top are horizontal. This is called an angular unconformity. Take out a white piece of paper and draw your own angular unconformity so you know what it is. That Sicker Point, James Hutton, he found an angular unconformity. Now let's take a look at the next one here. This is called a nonconformity. Here you got an unconformity surface represented by this wavy line, but this stippled pattern and the non-layered character of this indicates that this is igneous, plus the fact that it's cutting through sedimentary rocks. So you've got a different type of unconformity surface here. Below the unconformity surface here, you have igneous or metamorphic rocks, and above the unconformity surface, you have sedimentary rocks. See the difference? A geologist could stand 500 yards back and say, oh, I could see that's an angular unconformity. You got layered rocks above and below. That means you got sedimentary rocks above and below. That means it could be an angular unconformity. And it is an angular unconformity because they're dipping, that means they're tilting in different directions. But beneath the unconformity surface, they're dipping at an angle. On top, they're horizontal. Third type of unconformity is called a disconformity. And with a disconformity, you've got sedimentary rocks above and below the unconformity surface, but they are dipping in the same direction. They're tilting in the same direction. So these are your three kinds of unconformities, ladies and gentlemen, and you need to be able to recognize these. Nonconformity, angular unconformity, and disconformity. Now let's do a slightly more difficult relative dating question. And I bet you're going to get good at this, even though I feel you're a smart bunch. You're going to get this. So relative dating, let's do a more difficult one using unconformities now. And we will do something not too hard. Let's do this one here. Okay. Now we got an unconformity here. First, tell me what kind of unconformity this is. Do you have sedimentary rocks above and below? Yes. Are they dipping or tilting in different directions above and below? Yes. What type of unconformity is this red line? It is an angular unconformity, right? This is an angular unconformity. Let's evaluate this situation. G here is an angular unconformity. Now let's evaluate this. What are we looking at here in this cross section? Side view here. Well, bed H, E, B is the oldest because it's on the bottom, right? Then E, then H. Principle of what? Principle of superposition tells us that. But these beds are folded. These beds were originally horizontal and then folded, right? Bed D is younger than H, E, and B because it's on top, but it's on top of the unconformity, so it's also younger than the unconformity. Then bed F is younger than D, and bed A is the youngest here, right? But intrusion C, this must be igneous because it's not layered and it's cutting across these layers. So it must be younger than all that it cuts through, right? So let's do the relative dating here. See if you can get this answer here. And if you don't, keep on look at this picture. Just pause the video and see if you can get these exact answers. What happens first? You tell me. Bed B was deposited, right? Then what happened? Then bed E was deposited. Then what? Bed H was deposited. I should. I'm gonna make it even. Let me go around like this. Bed E was deposited. Then what happened? Then bed H was deposited. Remember, when you do your lab, put the first event on the bottom, not on the top, in relative dating. First event goes on the bottom. And then what happens? Then we had uplift and erosion forms a angular unconformity. Right? Isn't that what must have happened next? Because the unconformity cuts through H, E, and B. Then what happens? Then bed D was deposited. Oh, no. Then I missed one thing here. Damn it. I'm sorry to confuse you. Bed B was deposited. Bed E was deposited. Then bed H was deposited. I missed one thing here. Then what happened? Beds B, E, and H are folded, right? Then what happened? Then you had uplift and erosion forming an angular unconformity. Okay? Okay. Then what happened? Then 1, 2, 3, 4, 5, 6. Then what happened? Well, you tell me. Bed D was deposited. Then what happened? Bed F was deposited. Bed F is a sandstone. Then what happened? Bed A was deposited. Then what happened, ladies and gentlemen? Then igneous dike C cuts beds B, E, H, D, and F. There, ladies and gentlemen, is the correct answer. You need to be able to look at this picture and get this answer here. We just did some relative dating here. This one's more difficult than the first one that we did, which is a lot easier. But I'll do one more, and then we'll call it quits for tonight. Let's see if I get one more here. Let's do this one here, and then we'll call it quits for tonight. Okay, dashes mean shale, brick pattern is limestone, and dots mean sandstone. And this stippled pattern is plutonic rock. Then you got a fault here. This side moved down, and this side moved up due to an earthquake. Tell me what happened first. And put that on the bottom. Bed C was deposited. Then what happened? Bed B, the limestone, was deposited. Right? Then what happened? Bed A was deposited. There's no unconformity here. So then what happened? Then dike D cut through bed C, B, and A. Then what happened? Fault E cut through bed C, B, A, and dike D. Isn't that what must have happened? This side moved down and this side moved up. There was an earthquake. That was earthquake E happened last. Okay, we'll do progressively harder ones in the next video.